Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of quantum technology. So in this series today we will discuss the quantum device. What are the quantum device? They are on the high temperature, superconductivity, or they are used as a miniaturized device. So today we will discuss quantum devices. What basically quantum devices are? Quantum devices are defined as the system that utilize quantum effect and have application across various fields including metallurgy, where they can serve as reproducible standards in laboratory setting. So quantum device could be defined as a device whose functionality or principle of operation depends essentially on the quantum mechanical effect. All the quantum device is based on the formula of quantum mechanical effect. So a quantum device shall be defined more rigorously as a device that intentionally employs or harnesses quantum mechanical effect for its operation. Whenever these device operate, so it use the quantum mechanical effect. So in this lecture we will discuss about the quantum devices. So it is very limited to condensed matter devices, thus completely bypassing the natural use of quantum mechanics in the living organism. So a large number of devices already function based on the control of quantum mechanical interactions or effect. Means we are having a many devices in the real system which are based upon the quantum mechanical effect. So prominent example of these quantum devices are laser. As we all know that in the laser we use a photon from and we just use a quantum effect. So prominent example are the laser, light amplification by stimulated emission of radiation, and the SQUATE, that is a superconducting quantum interference device. Today we will discuss this device, how it operates, how we prepare this device, and what are application of SQUATE. But before that we will discuss what is the quantum devices. So a possibly large number awaits its commercialization or even their invention. So we define the quantum device which is having the reduced dimensionality. So these shall be understood as a device that rely on the structures that confines charge carriers in 1, 2 and all 3 dimensions. On the basis of that, we define the structure or we define the dimensionality of any material, any quantum material also. So these shall be understood as devices that rely on the structures that confine charge carriers in 1, 2 or all the 3 dimensions. So such devices or such systems are called quantum well, quantum wires, quantum boxes, or we can say quantum dot respectively. If we talk about the one dimension, then it is a quantum well. If we talk about it is a 2-dimensional, it is a quantum wire, and we are having the quantum dot by the confinement of the charge carrier in the material that define the dimensionality of the material. So the quantum effect that are used in the quantum devices are sorted by increasing order of complexity and decreasing order of fundamental understanding and employment in the devices. So quantum effect must be followed in these devices. So what are the fundamental understanding that are used and just increase the order of complexity and decreasing order of the fundamental understanding. So what is this? Number 1 is a single particle effect. Number 2 is a Paul exclusion principle. So third is a quantization of electronic state in confined potential. That is the most important part, where we are having a quantization of the electronic states in the confining potential. We define the charge carriers in the various energy levels. So fourth is a tunneling effect, how the tunneling takes place. As one of the application of the Schrodinger equation is a particle in box. After that, in the nanotechnology, we use the tunneling effect, crossing the barrier. Next is the spatial and temporal coherence of the wave function. Then 6 is the spin, how the spin work in the quantum entanglement, or how it is used in defining the system. So 7th is the quantum liquid, and 8th is the entanglement. So these are the points which keep into mind whenever we just prepare a quantum device. So the list, however, may not be exhaustive, as eventually any quantum mechanical effect, for example the quantization of other degree of the freedom or the still unexplored effect, may be used in the devices. On the basis of that, we define the quantization in the potential well. How we define the quantization in the quantum well, quantum wire, and in the quantum dot. So, if we talk about the quantization in the potential well, so quantum device of reduced dimensionality depend some way or another way on the presence of potential well that limits the motion of charge carriers in the dimensions compared to the bulk material. Means we define the confinement of the charge carriers in the dimensions by on the basis of the potential well, that is a quantization in the potential well. Now, the motion can be limited in one dimension within a quantum field. The motion can be limited in one dimension, where the confinement is in one dimension, then it is the quantum film, or we can say it is a quantum well. In the two dimension, when it is limited in the two dimension within the quantum wire, or in all the three dimension, if it is confined in all the three dimensions within the system, that is the quantum dot or a quantum box. These structures can be combined to double or multiple structures or even periodic arrays by confining the charge carriers in the material, so that we can change its dimensionality. So this is the table where we are having a structures with the 2, 1 or 0 dimensional confinement. So confinement of the motion to n dimension. If we talk about the second dimension or the 2 dimension, there is a quantum well, which is a double quantum well, and it is a super lattice. Combination of the two means we can combine the two quantum well, two dimensional materials we can combine, and we can get the quantum double quantum well. Moreover, there is a periodic structure, it is a super lattice, and another is the one dimension, that is a quantum wire pair, means multiple quantum wires we can pair. Another is the quantum wire array that can be prepared in the periodic structure of the material. 0 dimension, that is a quantum dot, that is quantum dot molecules, and we can prepare a periodic structure of the quantum dot in the form of the quantum dot chain or array. The confining potential can arise from applied spatially modulated electric potentials or the effect of band offsets in heterostructures or a combination of both, where we confine the charge carriers motion in the potential well. So the quantization depends on the size, shape and the barrier height of the confining potential. All the dimensions depends upon the size, shape and the barrier height of the confining potential. The potential will define then how the motion of the charge carrier in a system, that will define the dimensionality. So quantization depends on the size, shape and the barrier height of the confining potential. By controlling the barrier height between confinement structure, the degree of quantum mechanical coupling can be varied. So, whenever just we have the barrier height or the barrier height if it will change, then it will vary the quantum mechanical coupling. So, the simplest picture arises from the particle in the rectangular box with side lengths Lx, Ly and Lz and infinite barriers. The quantization energy is given by, this is very clear from the Schrodinger equation, that is E and X and Y and Z, which is equal to pi square h cut square divided by 2m nx square by lx square plus ny2 square divided by l square y plus ly square plus nz square divided by lz square. These are the dimensionality x, y, z, where the confinement of electron can be decided by these various lengths of the material where we can choose. Now we can just keep the potential barrier height, so we can confine the electron. So, with m being the effective mass of the particles, here we take the isotropic, and what is n? N is a quantum number that must be greater than or equal to the 1. If the confining potential is harmonic, the energy level are equidistant. So, E is equal to d by 2 plus n h cut omega. Omega is the frequency. Now we can see d. What is d? D is equal to 3 minus n shall be dimension of the confinement potential, with n being the number of unconfined dimensions. So, here we have the d is equal to 3 minus n shall be dimensions of the confined potential, but n is the unconfined dimension. So, quantum device encompass hardware leveraging quantum mechanics from fundamental component like quantum well lasers, quantum dot, single electron transistors and resonant tunneling diode to advanced quantum computer using the technology like superconducting, qubit or the tapped ion, photonic systems for computational sensing and combination. By using the dimensionality, by using this confinement, we can prepare these devices. So, one of the device we will discuss today, which is the SQUID, that is the quantum device, that SQUID, that is the superconducting quantum interference device. It is very easy to understand that here is using the superconductors plus we are using the quantum interference, and then we prepare the SQUID, that is a SQUID. What is this SQUID? This SQUID, superconducting quantum interference device, is a very sensitive magnetometer which is used to measure extremely weak magnetic field based on superconducting loops containing the Josephson junction. So, Josephson junction is used in the SQUID whenever we just find the magnetic field which is based on the superconducting loops that contains the Josephson junction. So, SQUIDs are sensitive enough to measure the field as low as 5 into 10 power minus 18 Tesla. With a few days of the average measurement, the noise levels are at a very low, and it will be in the hertz 10 to the power minus 12 hertz. So, for comparison, a typical refrigerator magnet produces 0.01 Tesla, that is 10 to the power minus 2 Tesla, and some processes in the animal produces very small magnetic field between the 10 to the minus 9 Tesla or 10 to the minus 6. So, SERF, atomic magnetometer, invented in the early 2000, are potentially more sensitive and do not require the cryogenic refrigeration, but are order of the magnitude larger in the size and must be operated in a near zero magnetic field. So, a SQUID is an extremely sensitive quantum device that is used to measure the very weak magnetic field, which is based upon the principle of superconductivity and quantum interference. So, squid are among the most sensitive detector ever built, showcasing real world application of quantum mechanics, and that is the quantum device. So, what is the history behind the squid? John Clark is a professor that has defined the Josephson junction for this discovery of the squid. So that has been he was from the Berkeley, and there he just developed to study of the superconductors, and the development of the squid was done by the John Clark. So he has participated in design of the squid magnetometer for a number of applications. So he relates having constructed his first Josephson junction after a discussion with the fellows, and then he just used the voltmeter capable of measuring the 10 femtovolts, that is 10 to minus 14 volts, which is very sensitive than the conventional semiconductor voltmeter. So Brian Josephson also working at the Cambridge, and he had earlier developed the concept of junction which bears his name. That's why it is the Josephson junction. He predicted the tunneling of the Cooper pairs of the electrons from superconductors through a thin insulating layer. So that this tunneling was verified a few months later at the Bell laboratory, and that was defined by the Phillips Ederson and John Rowell. So he defined the squid, and he defined the Josephson junction. Now this squid is of two types. First is the DC current, and second is the radio frequency. DC squid, where it used the two Josephson junctions, which is the most common and sensitive. Apart from this, RF squid use the one Josephson junction, that is a simple design. So RF squid can work only with the one Josephson junction, that is a superconducting tunnel junction. That is a Josephson junction is a superconducting tunnel junction, which might make them cheaper to produce, but are the less sensitive as compared to the DC squid. Now, what is the key principle behind it? The squid operates using the Josephson junction in a superconducting loop. Means we are using the superconducting loop as well as we are using the quantum interference. So squid operates using the Josephson junction in a superconducting loop. Another point is it is using the magnetic flux through the loop causes the quantum interference, changing the current or the voltage. So first Josephson junction, second is the magnetic flux that produces the quantum interference, and third the detection of the field that is in the range of 10 to the minus 15 Tesla. So what are the operating conditions? It requires cryogenic temperature, liquid nitrogen or the liquid helium we will use for this. Moreover, it is having the zero electrical resistance in the superconducting state. So before discussing the squid working operation, first we know what is the Josephson effect. In the Josephson effect, which is this where we use the phenomena that occurs when the two superconductors are placed in proximity with some barrier or restrictions between them. means we are having a two superconductors and they are placed in the proximity and they are having the some barrier or restrictions between them. So, the effect is named after the British physicist Brian Josephson, who predicted in 1962 the mathematical relationship for the current and the voltage across the weak link. So, it is an example of the macroscopic quantum phenomena. It is a macroscopic quantum phenomena because we are using the two superconductor and they are at a proximity distance. So, where the effects of the quantum mechanics are observed at ordinary rather than the atomic and the molecular scale. So, the Josephson effect has many practical applications because it exhibits a precise relationship between the different physical measurements like voltage and the frequency, which is highly accurate measurement that we can get through this Josephson junction. So, this is the Josephson effect, and this effect produces a current which is known as the supercurrent that flows continuously without any voltage applied across the device, and that device is the Josephson junction, that is the JJ. So, Josephson effect produces a current which is a supercurrent and that flow continuously in the circuit. Whenever we are not applying the voltage, still it is across the circuit. That is why it is a Josephson junction, or that is a JJ. So, this consists of two or more superconductors coupled by a weak link, and the weak link can be a thin insulating barrier which is known as a superconductor insulator superconductor junction. So, that is also known as SIS, or a short section of the non-superconducting material, that is the SNS, or a physical construction that weakens the superconductivity at a point of contact, that is the SCS. So, this junction have important application in the quantum mechanical circuit, which is the SQUAD, and the SQUAD use the JJ effect, and it use the JJ junction, and it is a superconducting qubits, and RSFQ digital electronics also use the Josephson junction. So, this is the DC. Now, here it is having the two types. So, the DC Josephson effect had just defined in the 1962. We defined the attributes of the super shorts, and that breaches in the insulating barrier leading to the direct conduction of the electrons between the superconductors. So, in the next lecture we will define the type of Josephson effect or the junction. Thank you very much.